So last time we talked about something called converse. All right. Do you remember what that means?
Do you know what that means? Oh, sorry.
I do not remember.
Oh, isn't that like the opposite of inverse or something? It means like,
Well, it sounds like inverse. It's actually quite related to that. It has to do with a logic statement. A logic statement. Have you learned anything about logic?
I mean, not from an educational level.
Oh, really? You don't have a taking a class on logic?
No.
Critical thinking. No, they haven't done that yet.
Okay. Yeah. So now in logic, the reason we say something logical is that there is a sequence. There is if something is true, then the other thing must be true. So something we write like as if let's say A is true, then B is true. Okay.
Yep.
All right. Now, for example, let's see. If trying to think of that. Now, if Earth is round, now what is the logic consequence? So one thing, a logic consequence, I'll say that then well, let's see. When Columbus trying to sail across Atlantic Ocean, what is his logic? So he assumed this, right?
He assumed that the Earth was round, so if you went to the left, you'd end up in India. So that was his thought process.
Yeah. So basically, if Earth is round, then he can reach India. India in the opposite direction, right?
Yep.
So in logic, we call, I mean, basically the reason we learn geometry is to learn the logic, learn how to use logic. So the condition we call hypothesis. And this is our conclusion. Okay.
Uh-huh.
All right. So we have this if then structure. So if A is true, then B is true. So the reason B is true is because A is true. So we are not saying if A is true. We're just saying that if A is true, then B has to be true. Good.
Yep.
Now the converse is basically saying the other way around. So basically we changed something flipped. Where is that? Okay. So is if B is true, then A is true. Okay. So this is a converse statement. So basically, just we shift the hypothesis and the conclusion. Good.
Yep.
Like here, this is the hypothesis, this is a conclusion. Now we use the conclusion as a hypothesis and the hypothesis as a conclusion. Now, this is not always true. That's why we need to prove it. Now, using Columbus as example, what's the converse of that statement? So remember the statement from the Columbus is that if Earth is round, then he can find India by traveling on the opposite direction, by crossing the Atlantic Ocean. Okay. Now, what's the converse of this? So the converse of that, if you can find India on the opposite direction, then the Earth must be round, right?
Mm-hmm.
So do you see the difference between what is a statement and what is a converse?
Yep. Yep.
Okay. Now, can you come up with a example? Yeah, it's going to be a challenge. Can you think of example in your life that you can see both? See the statement and the converse statement. Any?
I understand this class, I'll pass.
So say, if I understand this class, I will pass. Very good. So this is the hypothesis. This is a conclusion. Now, the converse is that if I pass this class, I understand. I'll say this. I understand geometry. Right? Good.
Yep.
Now, if well, let's assume this is true. If I understand geometry, I'll pass this class. The converse is, if I pass this class, I understand geometry. Now, is the converse true?
No.
Can you say that one more time?
Now, if this is true, if I understand this class, I will pass. Now, the converse is, if I pass this class, I understand geometry. So is the converse true? It's just something come to your mind. Doesn't matter right or wrong answer. Let's put it in that way. Let's just think you are in a regular public school. Now, if you understand geometry, you'll get A. Okay, let's say that one. If I understand geometry, I'll get A. Now, is that other way or converse true? If I get A, I understand geometry. Now we know the first one is true, right? If I understand geometry, I'll get A, right? Or let's assume that is true. In most cases now, if you understand geometry, you'll get A in a public school. But is the converse necessarily true?
No.
It's not necessarily true, right?
Yep.
Because you could get A without understand, what you have learned, or you probably will just memorize enough to get the A and then you forget everything about it. Good.
Yep. Yep.
Okay. So, and this is actually sometimes when you're dealing with real life, dealing with logic thinking, sometimes people confuse. They will think the converse is always true. Okay. And but this one is when we learn the geometry is to learn that the converse is not always necessarily true. So therefore, we have to prove it. Good. Even we prove the statement, but does not mean we can prove the converse. So for example, some here, if we can prove this is true, if I understand geometry, I'll get A. If we can prove this is true, it doesn't mean if I pass, if I get A, I understand geometry. It's not necessary. So we still have to prove this one. Good. Okay. So that's kind of get back to what we learned last time is that is proposition 18 is that there is two parts, okay? And this is the converse part, okay? There's original part is the converse part. And the original part is that any point in the perpendicular bisector of a segment is equal distance from the ends of the segment. So basically that if you have line segment A and B, then we have a perpendicular bisector, which means we cut this and cut that. And they're basically saying that any point on this line, which is a perpendicular bisector, we just pick any point, doesn't matter where you are. The distance from the point, let's say the point is E, to the both ends. So this and that have the same distance. That means this is congruent to that. So AE is congruent to EB. Sorry, EA is congruent to EB. Good.
Yep.
So we proved that last time. Okay. So, and that actually is pretty straightforward to prove. And remember, we're going to rely on the congruency of triangles a lot. So in this case, what we know, we call hypothesis, is that so we have a line segment C and D. Let's give a name to it. So we know CD is perpendicular to AB and AD at this point. This is our D. AD is congruent to DB. So that's hypothesis. And also E is any point on the line, any point on CD. So that's our hypothesis. Our conclusion is EA, that means EA is congruent EB. So we got hypothesis, we got conclusion. And that we know based on the convergency of triangles, we know we need to find out, okay, we know we know, okay, so we go into statement. We put the way we prove it like that. We got the statement, we got the reason. Okay, so we know that we know this is equal to that. That's basically it's given. We know AD is equal to DB. So that's given in a hypothesis. And we know this and that are congruent. So a angle ADE is congruent to angle BDE. So because both are right angles, and that's also given, is because CD is parallel, I mean, perpendicular to AB, that's given. So we got one side congruent, we got this angle congruent, that also the ED has to be equal to itself. So ED is congruent to ED itself. And so therefore we got what? Side, angle, and side. So we have, so therefore triangle ADE is congruent to triangle BDE. So we are based on side, angle, side. So because the triangle are congruent, we got this triangle and that triangle are congruent. So therefore, AE is congruent to, sorry, EA is congruent to EP. Good? Yeah, any question on this one? No? Okay. So now this is kind of a forward proof that we are given, we have a line segment AB from A and B, and we have a perpendicular bisector CD, and we are saying that any points on the line CD has equal distance to the two ends, to A and B. So let's clean this up. So we have this. We have if a CD is perpendicular bisector of AB. Perpendicular bisector of AB. Then we say that any points on the line on CD has equal distance to A and B. Okay, the two ends. So this is our hypothesis, is that CD is a perpendicular bisector. And this is our conclusion, is that any points on CD is equal distance to the ends of the segment, to A and B. And the converse of that is basically we shift this around. We're saying that if there is a point E that is equal distance has or equal distance to A and B, then it is on a perpendicular bisector. Perpendicular bisector. Okay.
Yep.
Okay, so now what we're saying here, if you graph it, is we have line segment. We got A and B. Then there's a point off the line. Let's say E here, which have equal distance from here to here. So we know this and that. So that's basically our hypothesis. EA is congruent to EB. And we have a conclusion that E is on or is on the perpendicular bisector. Okay, so basically it's the other way around. So conclusion and hypothesis is the other way around. So it's called converse. Okay. So how do we prove that? Now, in order to prove that, we have to draw a line here. We know we can draw from here to AB, we can draw a perpendicular line. And that's we learned before. We can draw a line perpendicular through this point, E. We can draw a perpendicular line through A and B. Okay.
Yep.
So because of that, we know, let's say that we have the point here is D. Okay. Now this line we call it CD. So we got, and we know that angle ADE is a right angle. It's a right angle, and that's but basically that's our given. That's what we did. We draw the line, and also BDE is also a right angle, and so therefore ADE is congruent to BDE. Okay, and this actually is one of a postulate. We got 5 postulate. Okay. So postulate is something like we don't need to prove. Is that something we take for granted? Okay. It's that we all of us can agree on. Okay. So we now have this angle and that angle got congruent, and we know this angle and that angle, that side are congruent. That's given. So EA is congruent to EB. That's given. So this is a hypotenuse, right? Because this is a right angle. So this is a hypotenuse, and this is a hypotenuse. And we know this ED is congruent to itself. And that's actually one of the postulate. And therefore, remember we had a theorem, a proposition we proved before. If we have 2 right triangles, as long as the hypotenuse are congruent and one of the legs is congruent. So we have that. First of all, we know it's right angle. And then we know this and that are congruent. EA and EB are congruent, that's given. And ED is by itself. So itself will equal to each other. So, but ED is a leg of the triangle, right triangle. So therefore, based on the previous theorem, we know that these 2 ADE are congruent to triangle BDE. BE. Now, because they're congruent, so we know A, D is congruent to BD. So we know this has that, they're congruent. So now we know this line, first of all, we know is perpendicular. And second of all, we know this line actually cut AB into two equal parts. So therefore, and E is on this line. So CD is a perpendicular bisector. And we know that E is on CD. So that's how we prove that E is indeed on the perpendicular bisector. Good?
Yep.
Yeah. So again, when we learn geometry, is learn how to think logically. Sometimes it seems tedious, but that kind of help us. I mean, it's a discipline for us to think logically, because we as humans, that is something not most time we reason based on our feeling, but we know that is if we're based on the feeling, that is very unreliable. So that's why we learn science, we learn geometry, is to help us to have the discipline that everything has to have a reason. Okay, everything we come down to, if we say it is true, and it has to follow the logic, it has to go through. I mean, what kind, if we want to prove something true, we have to always trace the back either to the axioms, or we trace back to a theorem we have proved before. Good?
Yep.
All right. So I will see you next time. Okay.
Thank you. Thank you.
Bye.
Bye.